Here we go. Sorry about that. It's sometimes the most simple technology that fails, anyways. This talk will be about you know, sometimes it'll be about Coreboot and an open source boot system, and my mind just went blank, which is a bit unfortunate. Yeah, I hope you enjoy it, and we have a bit of overtime if you feel like that in the end. And you can start now.
Thanks.
Sorry about that.
All right, so I'm going to talk a bit about Coreboot and related things. Okay, let's figure out the sound. Where can I go? I can't go there. Okay. So, first of all, who am I? A look at the state of firmware on the PC. First of all, what was there before, what we have right now, and where I think we should go. Going to talk about payloads, which is an important concept in Coreboot. Some auxiliary tools developed by the same people developing Coreboot. I have 2 nice demos that I hope are going to work on real hardware. Some security thoughts, attacks, defenses. A conclusion, some thanks, and links. So my name is Peter Stuge. I'm a self-employed consultant in Sweden, in Malmö, southern Sweden. I know software, hardware, security, and a bit more. I like anything embedded and open source. I discovered Coreboot back in 2001. It was called LinuxBIOS at the time. I was working on building a set-top box for my employer. And it was x86 based, and we needed a firmware. So I thought LinuxBIOS looked really good. Unfortunately, we didn't end up using it, but I stuck with the project. Until 2006, I mostly hung out on the mailing list trying to not say all that much, but scope out what was going on and learn as much as I could. I started getting involved in Coreboot for real at the developer meeting that was held in Hamburg in 2006 in October. These days I work on flashrom, MSR tool, FILO, a bit of K8, that's AMD 64. Version 3 of Coreboot, some support and marketing. So looking back, in the beginning of the PC we had the BIOS, and we had an 8086 CPU, which did stuff in real mode. And a show of hands, how many people know about real mode and how it works? Excellent, that's about, quick, maybe third, maybe half. Real mode is a processor mode where you have 16-bit registers, so the only data you can handle, the largest data you can handle is 16 bits, from 0 to 65,536. But you had 20-bit addressing, so you could use a little bit more memory than 64K. In the first machines, there were 2 tape drives that had the operating system and that were going to be booted from. So the BIOS started out really as hardware abstraction. It created a unified interface for accessing these tape drives, loading the software off the tape drive into RAM. And it also did some console stuff, keyboard, video. It had a code for handling the serial port. And all of this happened through software interrupts, where the operating system triggers a special interrupt instruction. The system then jumps into BIOS code and does whatever it needs to do to access the hardware and returns the result to the operating system. This is a task that is pretty slow in the 8086 real mode. So the present, we still have BIOS software in our PCs today, and it's still real mode. It's still 16-bit, and it still has 20-bit addressing. Everything works through interrupt services today as well. There's hundreds of them. The API of the BIOS has just grown and grown and grown. It does floppy and hard drive abstraction. These are just some examples. It does power management abstraction, which is interesting. We're going to come back to that in a bit. But really, the BIOS today, with modern operating systems, it mainly does hardware initialization at the time you turn on the PC, and it starts up the operating system. All the old stuff, the console drivers, the serial port drivers, the floppy and hard drive abstraction, it isn't used by the operating system. It's used by the bootloader to get the operating system started and get the operating system running. But once started up, Linux has all its own drivers for everything. Windows does as well. No modern operating system really calls back into the BIOS using these interrupt services anymore. So what's the problem with this? Well, besides the fact that it's about 30 years old, the BIOS used to be this library where the operating system always initiated the call, and the BIOS was just used to perform whatever action was desired. But then there were developments. The first laptops started coming out, and when you close the laptop lid, you want the system to sort of pause or hibernate and enter APM. This was all realized using system management mode, which is a pretty interesting topic. We're going to go into that a bit. How many people know about system management mode? 3. Excellent, excellent. So this was introduced in the 386 SL CPU, pretty old. For laptops, it was Intel's mobile 386 CPU. What happens is, in the beginning, you configure, or the BIOS configures, a handler for events, system management events. And when this event is triggered, the processor stops whatever it's doing completely. It saves off everything it knows about the current state, and it jumps to this pre-configured code, this pre-configured handler. And it's literally like time stands still. The software that was running on the CPU has no way of knowing that the CPU has been into system management mode to do something and then come back. This was all triggered in the beginning by an electrical signal. A new electrical signal was introduced, the system management interrupt signal. But it could also be triggered by software. You can set up SMI traps that invoke this system management mode from an I/O port access or from writes to whatever memory locations you specify. And this is used quite a lot. So this was APM, and APM wasn't really all that bad. It wasn't so powerful, but it was a pretty nice design for the time. And then came ACPI, which we all love. This is the Advanced Configuration and Power Interface Specification by friends at HP and Intel, Microsoft, Phoenix, and Toshiba. The document I found is revision 3 from 2006, 600 odd pages, and among other things, it specifies a virtual machine, has its own bytecode, and it runs in the BIOS. So it's in the BIOS, it's outside the operating system. Really outside the operating system. Yes, at first they did it that way, but it turned out it was too slow. The numbers I've seen was a 5% performance hit from having this virtual machine in the BIOS. So the only solution they came up with was moving the virtual machine into the operating system, and Linux started doing this circa 2001. I've seen the figure, 90,000 lines of code to implement this virtual machine, and the fun part is that it still operates completely outside the operating system's security model, because that's the way it was designed to run, and that's the only way it will run. So what do I think about the future? Well, BIOS overview, 78, it was used for tape I/O abstraction. 2008, we have just gobs and gobs of function calls or API calls, and it's real mode. I listened to a presentation from one commercial BIOS vendor. There are only 2 out there at the moment, so they're a bit difficult to work with. They described how their code base has 4,300 files, source code files, in assembly, but it's modular, so it's really easy to work with. There's also EFI. Is starting to pop up here and there. It's already out in Intel Macs and some other Intel machines as well. It's really like a small operating system. Reminds a lot of the old DOS. Has networking stacks. It has a lot of other nice features if you want to develop software and plug into EFI and run during the boot. It's sort of open. The idea is that anyone can download the specs and write these kind of plugins for EFI. But it's not really possible to see what goes on in the core of EFI. Intel doesn't tell you that. So it could be using system management mode for all we know. The Tiana core codebase, which is the development kit for EFI, is about 250 megabytes. Could be compared with the Linux kernel, which is about 50 megabytes. There's a lot of other bootloaders as well. Grub you've heard about. And Grub is really a bootloader, as is LiLo. RedBoot is a bootloader as well, firmware, if you will. It's based on the ECOS operating system, real-time embedded operating system. But unlike EFI, it's really similar to EFI in that respect. But unlike EFI, it's really open source. ECOS is completely open source. There's also U-Boot, which is a firmware for mostly used in smaller systems, ARM, MIPS, power machines. So I say Coreboot is a BIOS replacement. And the BIOS, it does the hardware initialization, and it starts up the operating system. We saw that. Coreboot really only does the first part. It does hardware initialization and nothing else. Then it hands over to a separate program, which is called a payload. The payload takes over and does whatever is supposed to happen. It can start up the operating system, or it can be an application even. Coreboot and the payload, they go together into a single file that is programmed into the flash chip, where the BIOS used to be. So what kind of payloads can we get? We have a lot of bootloaders for different operating systems and storage media. We have FILO, which I mentioned already. It's used to boot Linux or multi-boot kernels from local storage, hard drive or CD-ROM, compact flash if you have that on a IDE bus. EtherBoot, GPXE, maybe you've heard of. You can use that to boot kernels off the network. SeaBIOS is an open source BIOS implementation. So if you really want or, well, maybe need the BIOS stuff, you can still have that, but at least you can have it open source and you can have it in C. Hopefully you won't need it, but for now it's needed to do BSD and Mac OS and DOS, and we've tested it with Windows XP and Vista as well, so it's good. You can also have open firmware as a bootloader payload if you want to, or you can have Linux, which is really the big win. That was also the original idea with Coreboot, or LinuxBIOS, as it was called from the beginning. It started out in 1999 at the Los Alamos National Laboratory in the US. A guy named Ron Minnick. He was building a computing cluster with thousands of PC nodes, and he realized that he didn't want the keyboard error, press F1 to continue on all of his machines, so he did the only reasonable thing and started writing his own firmware. Yeah. The good thing about that is that Linux has a bunch of drivers for whatever hardware you can imagine, and if you can put that into your firmware, then you have access to booting from whatever. You can boot from wireless, you can boot from iSCSI, you can boot from MirrorNet, which is what they used. You can boot from InfiniBand, which is not so easy to do with a BIOS maybe, and also not as fast. Grub2 is also up there. It's also a bootloader. We've had some difficulties getting Coreboot 2, or sorry, getting Coreboot support into Grub2, but it's finally getting there. But not only bootloaders, the payload could be utilities of some sort. It could be memtest86, RAM test tool, which is also used by us developers to see that we've really configured the machine properly. Because nothing, the most difficult part of initializing hardware is getting the RAM configuration correct, and memtest will always show us if we've made some mistakes. Coreinfo is a nice small utility, has some basic system information, looks at the PCI devices. We're going to see that in the demo a bit later, I hope. And here it says Linux again, because, okay, so you can have a kernel in your firmware, but you could also put an init ramfs in the kernel, and then you can load up, I don't know, whatever applications you want to have there, as long as you have room in your flash chip. Rescue utilities, and at least a shell, a prompt that you're familiar with. Ron, the guy who started this thing, he likes to bash open firmware because of the OK prompt. I don't know if you've seen it. When an open firmware machine has a problem during boot, it stops and the prompt says OK. But in reality, things aren't really OK. So he really likes to have a Linux system and a shell that he's familiar with during the boot process, in case anything goes wrong. And I mentioned we can do applications as payloads. We can have stuff like Tint, which we'll have a look at later. It's a nice little game. Bayou is really important to mention because Coreboot can really only start one payload, a single payload. But maybe that's not enough. We have a really big flash chip, so we want to stuff a whole bunch of these guys in there. Then we use Bayou to first of all pack several different payloads into one, and then we use Bayou as the Coreboot payload. Bayou gives us either an interactive menu that we're going to have a look at, or you can script it to do stuff in sequence and have some control over the boot process. Both Tint and Bayou and coreinfo are realized through libpayload, which is the C library. Really simple C library, but still it's not complete, but it has a lot of functionality. If you have a simple C application, you can just link with libpayload using the wrappers. We have some wrappers in the package. You run LP GCC instead of GCC. Out comes a payload binary instead of your normal ELF user space application. And we even have a curses implementation, which is pretty nice in libpayload. So you can have a nice user interface as well. I mentioned some auxiliary tools. We have buildrom, which is important because, so we have Coreboot, we have several versions of Coreboot. We have a whole bunch of payloads. The payloads need to be configured. Coreboot needs to be configured. It depends on which mainboard you have. This can get a bit tricky, but buildrom will take care of most of that for you. You just have to say, I have this mainboard, this flash chip, I want this payload, and go. Buildrom will gather everything up and build you the final working ROM file that you need to flash into your chip. Make elf image is at the moment the key tool for turning a Linux kernel into a payload. Just needs to add a little bit of glue. We have nvramtool that is used to peek and poke at bits in the 256 bytes of nvram that is in every PC. Good for storing boot time settings and passwords maybe, or maybe not. Superiotool, great for peeking poking at the superio chip, which is the piece of hardware that implements all the old school ports like PS2 keyboard, parallel ports, serial ports. What else? Yeah, GPIOs if you have any. Intel tool and MSR tool, they're more complex register dumping tools, tweaking tools for finding out state in a system before you have Coreboot and after you have Coreboot, or while you're working on developing Coreboot to see what you're doing wrong. And we have a special tool called flashrom, which I do some work on, and I like it a lot. It's a BIOS upgrade tool for Linux, or BSD, or Mac OS X, or Solaris. So you don't have to reboot using this sad old DOS floppy that doesn't work anymore in order to upgrade your BIOS. You can just do it from Linux. Flashrom also supports cross-flashing, which is an important feature. The DOS utility, it often checks that, okay, you want to flash this image onto this mainboard, but I don't know, this doesn't look like a match. I don't think you're going to be allowed to do this. You might end up bricking your board. This has a real sour taste, I think. So we don't limit the users in that kind of a way. If you want to flash a bitmap into your boot flash, that's fine. But please make a backup first. Seriously though, it's a really, really good feature, because if you do flash a bitmap into your boot chip, you can still yank the chip out, put it into another machine while the other machine is running, and run flashrom to reprogram the contents, restore the contents of your flash chip and get the first machine booting again. Flashrom supports a whole bunch of flash chips, hundreds, 66 something chipsets, and more than 25 mainboards with small variations. A lot of mainboard manufacturers, they start from a reference design from the chipset manufacturer, and then they make small tweaks. So if we make flashrom work on one of them, it will work on all of them. And there's this neat idea called push-pin flash. I so wish that I had come up with this. So these flash chips, they're can be a bit tiny. They're maybe 2 by 2 centimeters or so. And if you have a whole bunch of them, it can be tricky to keep track of them, and you need tools for pulling them out, and it's not always easy to get them in to the socket correctly. So take a thumbtack, pull out the pin, and glue the plastic knob on top of the flash chip, and you have a nice handle, and you can color code. It's pure genius. So demo time. I'm going to show you Coreboot version 3 running on an Alex 1C CPU board. That's an AMD Geode LX CPU. It's a PC system with an AMD CPU, 256 megabytes of RAM, made by a Swiss company. Pretty nice hardware. Let's see. So looking at the output here, we have a serial console, and I release reset now. We see Coreboot starting up, and it finds the Linux kernel. The Linux kernel is starting now, and we're up. Yes, it worked. You want to see it again? No. Okay. So this second demo is a bit more, has a bit more eye candy, and I'm actually going to move this over now. I tested this earlier today, so it should hopefully still work. Come on, don't be a hater. Oops. Okay. So apparently I can't really turn. Yeah, okay, I can turn. So this is Bayou, payload chooser, and into this Bayou I've built 3 different payloads. System information is coreinfo. Yeah, okay, not perfect image. We're missing a top row. We see the CPU here. It's made by AMD. It's the Geode. Some CPU flags. We can look at the PCI devices and the config-based registers. Great for debugging, checking out that Coreboot set it up correctly. We have the nvram to look at the settings. It's just hex, but still better than nothing. And the Coreboot information. We can see here this is the PC Engine's LX1C, and this is running a Coreboot version 2 that I built back in September. So we're done with that. We see that everything is configured correctly. We get a small reward. And when we're done playing Tetris, let's go back to here and see if we can boot the kernel, and we're up again. So, yeah, demo. Okay, what about security? Are there any issues with this, or are there any issues during boot that we should be aware of? Jake Applebaum had a great talk just before me up in Saarland about cold boot attacks, where if you didn't see it, the idea is to extract data from RAM chips even though you powered the machine off, and this works. What can we do to facilitate this attack in Coreboot? Well, because we're doing the RAM initialization, we can stop right after RAM initialization is complete and do whatever we want. It's open source, so go ahead and have some fun. Do some special dump routines. We can even utilize another trick, which is called cache as RAM, to not have to use any RAM at all, so we can really extract every single byte of data that is in RAM. Thanks to the system management mode, we can do TPM emulation or TPM sharing. So you want to listen to some music, and it's all locked up in this fruit box in the corner. You can sort of export that TPM in the corner and have that accessible over the network so that all your machines are able to play the music, for example. Or you can do an SMM rootkit, which I think Ben Kurtz is going to talk about tomorrow. Remote disks, fun, because, well, system management mode, you have full control. You could, for example, start using the CPU fans as a waveform output to play sound. If you think that's fun. And you can, of course, lock the user out to some degree and force them to play Tint until they win before they're allowed to start their system. And, okay, what can we do about this on the defense side? Because, of course, we can use it for defense as well. Because, precisely because we're controlling the RAM configuration, we can ensure that memory is scrubbed immediately upon boot, as soon as the memory is initialized. And if we're using ACPI also, we can make sure that the RAM is scrubbed before shutting down. Even better. We could do intrusion detection if there's an available signal, electrical signal, a pin somewhere that we can read, and if someone opens the case, well, we scrub the memory and feel pretty good about ourselves. Filter ACPI, make sure that the ACPI code that comes from the BIOS vendor and is running outside the operating system security model doesn't do stuff that we don't want to do, because we're in control, really. Access controls require certain hard drives or other peripherals to be present with certain serial numbers before booting is allowed. Virtualization, to some degree, encrypts data on the fly and make sure that the flash chip is locked down. So, conclusion. Good stuff about Coreboot. We get a pretty quick, snappy startup time. That's nice. We all want that. It's open source, as opposed to the two commercial BIOS vendors. Coreboot itself is licensed GPL, whereas libpayload is BSD licensed, so it can be linked to whatever application you're working on. Auditability, of course, you can look at the code and see what's actually going on. And it's written in C, and it's not 4,300 files. If you're the kind of developer that needs to do BIOS extension or firmware extension, then Coreboot is great because we just have one source tree for all the mainboards, whereas said BIOS vendor, they actually fork the entire source tree of their 4,000 files for each mainboard. And this means that new features added to one mainboard doesn't always get included on other mainboards, but they think it's a feature because when you have this board out in production and the BIOS software out in production, and you only want to make a small change, then you don't want to have to pull in all the changes from all the other mainboards, but you want to do just a small change and send out a new version of the BIOS. I guess they don't know about tags and branches. So the one source tree makes reusability and extensibility a key factor, I think, in Coreboot. We still have work to do, of course. We need more testing. There's a great testing framework that Google sponsored development of that actually does runtime testing of every single commit on actual hardware. The only catch is that someone has to hook up that hardware to the testing system, and we don't have very many of those setups yet. I'm a perfectionist, so I dare say that few boards are really 100% working. Maybe just one. It's an Asus K8 M890 board. I don't remember the exact model. But there are a lot of main boards, both embedded desktop and server boards, that are not very far behind. ACPI is one thing that we are getting better at. It's pretty hideous, but we really can't do without it for some operating systems. I hope that will change in the future. I so hope that will change. And I think Coreboot will actually be play a big part in that. I hope others agree with me too. And I often get a question about laptops, because everyone wants this on their laptops. The hard part about laptops, it's doable, but in laptops, even if the chipset and the CPU is really similar to a desktop or a server, well, maybe mostly a desktop, there's this extra small chip, a microcontroller, that is doing some special tasks, handling the whatever function keys you have on the laptop, and handling the lid open-close buttons, and some power management, battery charging, etc. The sad fact is that manufacturers like HP or Dell or whoever, they don't know really very much about how this embedded controller works, because it's developed by two guys sitting at their ODM, the design manufacturer in Taiwan. And they don't really have any channels to get documentation out or to get some contacts through so that we can talk to them. And that, of course, means massive reverse engineering work, which is doable, but it takes a lot of time and effort. We're hoping to find some vendor that is interested in getting Coreboot onto a laptop, and we're working on it, but progress is a bit slow. If you know any vendors that are interested, please come talk to me. But there's a lot of fun stuff ahead. So I want to say some personal thanks, in particular to Uwe Hermann and Jacob Appelbaum, because their research on, Jake's research on cold boot and Uwe's RAM dumping stuff in Coreboot led to me ending up at the Meteorographics camp this summer, which was a fantastic time in Italy. And I also want to say a huge thanks to the Chaos Angles, because this event is probably the best event in Europe, and without their work it wouldn't be possible. So we have some information up on the web. If this wasn't enough, we have the mailing list, of course, and an IRC channel. Please come talk to us or me. Coreboot.org/FILO/libpayload, EtherBoot. Most of the stuff I've been talking about has its own wiki page. And there's a search function, of course, on the wiki as well. Do we have any questions? Do we have time for questions?
Yes, I certainly do have some time for questions.
Okay. Any questions? I see over there, over there.
Just make sure it's working. Yeah, it is.
I have two questions. The first one is, I own the same board, it's Alex 1C, but there is JTAG access. So my question is, how have you flashed the chip? Because it's not a flash chip that you can just take out. It's soldered on the board.
Excellent question.
And second is, yeah, I think I forgot the second question.
So let me answer your first question, and maybe you'll think of the second one again. It says there, I'm doing a workshop tomorrow evening at 10, where we are going to play around with the Alex1C and flash Coreboot into it if you want to, if you have the board. The Alex boards are really hack friendly because they have a special jumper, and you can order a spare flash chip from the manufacturer for €4, I think, which you just plug on to the header and it overrides the flash chip which is on the main board. Really easy to work with. If you have a desktop mainboard or any other mainboard that doesn't have this feature, of course it can get a bit more tricky if you don't have a socket. If you're skilled with soldering or you know someone who is, just take off the flash chip and solder a socket on there instead. It's not crazy impossible, it's doable. But in the end, if the chip is soldered down, and also there are some surface mount chips that are a bit difficult to work with, then maybe it's better to look for another similar board.
Okay, the second question was about JTAG. Have you investigated how JTAG is? I mean, on the Alex you have JTAG access, but on other laptops sometimes the CPU has JTAG pins, but sometimes they are not wired on the board. And have you investigated how to get Coreboot flashed with JTAG?
Well, okay, getting it flashed with JTAG may or may not be difficult, a bit depending on how the board is laid out and how the JTAG chain looks. The thing with JTAG, if anyone doesn't know, it's a sort of a serial bus where all the major hardware components on the main board are connected together in a chain. And if you know how each component works inside, you can control the component completely using JTAG. If it's a CPU and you know how the CPU works, you can single-step instructions over JTAG. You can inspect all registers. It's really a superb hardware debugger. The catch is that you need to know how the chip works inside. And getting those description files for the interesting components is next to impossible. Or if you're going to do it yourself. The option is, of course, to buy a Lauterbach or some other equipment for maybe a few €100,000, but that's not really within the reach of enthusiasts, unfortunately. If you're doing a business project, maybe, but it's still pretty expensive equipment. And JTAG on x86 systems, unfortunately, it has a high threshold before it's usable. Did that answer your question? Sorry? Yeah, okay.
There's a question over here as well.
How large are these flash chips? Because you had virtualization on there. Would it actually be feasible to implement a hypervisor in a flash chip?
The Xbox 360 has a hypervisor in mask ROM, so yeah, sure. Just depends on how competent it should be. But yeah, a simple hypervisor, no problem. To answer the question, how big are these flash chips? That's also a good question. It varies from, I would say, 4 megabits to 16 megabit on the main boards that are out today, and flash chip size is measured in bits, so that's half a megabyte to up to 2 megabytes. Half a megabyte is pretty tight if you want to squeeze a Linux kernel in there, but 2 megabytes is already somewhat roomy, and most of the times these flash chip interfaces, they also allow you to put an even bigger flash chip on there if you only order one, and the cost isn't, there's no real big difference in cost for these flash chips. So if you have a socket and you can fit a bigger flash chip on there, go for the largest one you can find so that you can play around.
So my question is, what has Coreboot done as... I'm ready.
There, okay.
What has Coreboot done as to system management mode? Is there anything interesting about that Coreboot has implemented?
Good question. We have 2 implementations of system management mode code in Coreboot. I mentioned that system management mode is actually used quite a lot, and in particular on the geode, AMD geode, which is used on the Alex board. The normal way of booting the system or bringing up the geode CPU is to virtualize a number of PCI devices using system management mode. So, and AMD has released source code to that implementation, and they have also started work on porting it over from the Microsoft development tools, the macro assembler and so on, onto open source GNU tools. That second version doesn't run yet, but the code is there to look at and to hack on. And we also have a second implementation of system management mode handlers in Coreboot, which is for the Intel 945 chipset and coupled with the Core, any Core 2 or Core CPU. So there are 2 different frameworks for system management mode experiments if you want to do those. Answer your question? Yeah.
In BIOS and Open Firmware, it's possible to load extension ROMs. So how is the concept of integrating like future hardware concepts into Coreboot in the future?
That's a really good question. At the moment, we can use SeaBIOS to run existing option ROMs. We can also run them in an emulator, x86EMU, or we can run them in VM86 mode. Personally, I just have one idea for this, for the really long term. I want to run Linux as my bootloader, and sorry, I of course want Linux to have drivers or have the software to initialize all this hardware. So I don't know if you've heard about this, but Fabrice Bellard, the guy who has done a lot of work on QEMU, he's also written a C compiler called TCC. TCC is able to compile a full Linux kernel in, I think it was 14 seconds. Pretty impressive. So my sort of idea for something that would work is to have, first of all, Linux software, be it a kernel module, preferably not, but worst case kernel module or a simple user space application, do whatever the option ROM does today as far as initializing the hardware. And then if you have Coreboot and a kernel in your server, your SCSI card fries and you have a replacement in the shell, on the shelf, but it's not exactly the same model you need in your driver. Okay, out with the old one, plug the new one in. You boot up, plug a USB drive in with a kernel source. TCC builds the new driver for your kernel. It takes maybe 10 seconds. Reboot again, or maybe just load the module into your Linux kernel because you're in utility mode right now. And kexec your kernel, which is your main system kernel, which is on the RAID drive, and off you go. That's my vision. I would really like that. A lot of work hasn't been done yet, but
it's more a solution for
Well, it could all be automated. I mean, if you can have a distribution CD-ROM that at runtime determines which modules to load depending on the hardware configuration, then you could have the same, use the same method to determine which drivers you need to compile. Oh, okay, so you have this new hardware that I didn't know about. You need this driver. Let me compile it. Okay, now I'm done. Is it okay if I load the driver? Yeah, go ahead. Okay, let's boot.
I was amazed to hear about cross-flashing. Do you change chips in a running system?
Yes. That is actually perfectly safe. The flash chip is really only used when the BIOS is run. Even one of the early things the BIOS does is it copies the contents of the flash chip into RAM, because the flash chip access is really slow, so it would take forever if the BIOS was running out of the flash chip. And that means the flash chip is just sitting there on the bus, and no one is talking to it. So if you pull it out, the system will continue running along and be none the wiser. It's, of course, you have to be careful to not, I don't know, stuff pens and paper clips and so on onto the CPU or the socket for the flash chip. But if you're careful and maybe use the push pin flash, it's perfectly fine to hot swap flash chips. We do this all the time.
Any more questions? Oh,
One more question there.
Payload utilities, are they portable to other platforms?
What utilities, for example?
The flashrom,
Flashrom.
using it in EtherBoot, gPXE,
And what other platforms do you mean?
like gPXE or EtherBoot.
Yes. What?
The tool flashrom, can I use it to flash memory on Ethernet cards?
Not at the moment, no. Not at the moment, but we're actually looking right now at implementing a sort of programmer plug-in interface in flashrom, really simple, but still, that would make it possible to write a simple driver for the Ethernet card in order to be able to reflash the chip there. But there are some, I've seen some other utilities to do exactly that, which are completely standalone utilities and work very well. Flashrom doesn't do it at the moment, though.
In gPXE, you can boot over at least in the. It's possible to boot over Wi-Fi. There is a Prism 2. There is a very old code for booting over Wi-Fi.
Okay.
But and one of the major issue in gPXE is that you need to backport some wireless driver from the Linux kernel to gPXE. It's kind of a work. Do you think it would be possible to boot from Wi-Fi with the LinuxBIOS and some wireless drivers? Or it's
Yes, definitely, and this is why Ron is such a, and me also, is such a big fan of using Linux as the bootloader, because you have the hardware drivers in Linux. You know they work because you're running them in the operating system, but with open firmware or with Grub2 or with FILO or whatever, LiLo, you end up writing your own drivers again for the same hardware, and that's such a waste of time because you have these nice shiny drivers in the kernel that work. So that's exactly the point of using Linux as a bootloader in order to reuse the drivers that are known to work.
And what is the status of net booting? Do you rely on gPXE or you have also your own net booting, or how do you do?
I think I understand your question. How to do this then? Well, you need a kernel with the wireless drivers, and you would use that kernel as a payload for Coreboot. But that's not enough because the kernel is going to want to mount the root, so you also have to tell the kernel how to find the root, how to configure the networking interface, how to associate, etc. So you need a small initramfs or initram disk with the wireless utils and to store your configuration in, and that will then configure the network and mount the root file system wherever it is. But that's sort of out of the scope of Coreboot. Coreboot really only goes until the payload boundary, and then it's someone else's world and system. Is that an answer? Okay.
Any more questions?
So it seems no more questions. If you have anything else you want to talk to me about, feel free to come up. Again, the workshop tomorrow at 10 p.m. if you want to have a look at how we build Coreboot and what we can do to put it on the LX1Z. Thanks a lot.